Welcome to the introductory video into enthalpy and enthalpy change. Now there's quite a bit you need to know about enthalpy and changes in enthalpy and a few calculations to go with it. But unless you've got a fundamental understanding of what enthalpy is to start with, then those calculations aren't really going to make much sense to you. So that's what this tutorial is all about. So first of all, what is enthalpy? Well, it's the heat energy stored within a chemical system. Now, what do I mean by that? Well, there's energy stored within chemicals. Now, you've come across chemical energy before. This is technically what that is. Now, where is that energy stored? Well, it's stored in bonds. So you could be looking at, let's say, a covalent bond, a straightforward covalent bond, and even in something like water, for example, where there's covalent bonds, energy is stored within those bonds. Likewise, in things like metals, in metals, there's energy in the attractions between those delocalized electrons and positive ions. Speaking of ions, let's say in salts, there's Na and Cl-, sodium chloride. There's electrostatic attractions between those as well. There's energy involved there. But equally between gases, let's say we've got methane molecules like so, there's energy stored within those. But even with the intermolecular forces between them, there's energy stored in there. So in any chemical system, there's energy stored in there. Okay, and we refer to it as heat energy because that's how we're able to measure it. So within all the different bonds and intermolecular forces, there's energy stored within a chemical system. But we can't measure that directly, okay? What we can measure, however, is the change in enthalpy during a chemical reaction. So what is enthalpy change? So enthalpy change is the heat energy exchange with the surroundings in a reaction. So whilst we can't measure the enthalpy stored within the bonds as a chemical system exists, when a chemical reaction occurs and those chemicals change when you turn your reactants into products, what we can do is measure that change in energy. And of course, that energy is measured in the exchange of heat. So either heat is given out during a reaction or heat is taken in. It really depends on how much energy it takes to break these bonds, the energy that needs to go in, and how much energy is released when new bonds form. So that's our enthalpy change. And the delta here, the little triangle, that means change in. Delta means difference in enthalpy in between our reactants and our products. But we can actually go one further, okay? What we see a lot of the time is delta H written like so, with a little theta above it. What that means is at standard temperature and pressure, STP. Now, what are those standard temperatures and pressures? 100 kilopascals, or 1 atmospheric pressure, and 298 Kelvin, or 25 degrees Celsius. We say this because at different temperatures and different pressures, our enthalpy change can alter. So if we have a standard temperature and pressure that we use, we can actually compare enthalpy changes of reactions using those values there. So that's our enthalpy change. How much energy does it take to break those bonds and how much energy is released? And it's a balance between the two, the change in a reaction. Now, if you cast your minds back to GCSE, you will know that reactions release energy or take energy in. Now, those are known as exothermic and endothermic reactions. So what does delta H look like for an exothermic and an endothermic reaction? So you'll probably recall that in an exothermic reaction, heat energy is given out to the surroundings. Temperature increases. That's because energy has overall been given out by the reaction, causing the surroundings, their temperature, to increase. Of course, the opposite is true here. If energy is drawn in from the surroundings, temperature in those surroundings decreases. Okay, so whilst we're not measuring the enthalpy within the system, we're measuring the change in enthalpy depending on whether the temperature goes up or the temperature goes down. So let's have a look at that in terms of delta H and what that means for the values of delta H for exothermic and endothermic reactions. What we're going to look at here are energy profile diagrams. So we look at the profile of energy and what happens in terms of the energy exchange, the delta H, the difference in enthalpy for an exo and endothermic reaction. So I'm going to go ahead and draw the energy profile diagram for an exothermic reaction. So what we've got here is the energy stored in the system. Okay, so think of this like the energy that's stored within the bonds and the intermolecular forces in the system. So energy increases going up here. So here are our reactants with quite a lot of energy stored inside them. Let's say this reaction proceeds, and as we go along, we need to put in a bit of energy to break those bonds, but overall, the energy in the system has gone down. Okay, we've got less energy in our products stored within the bonds than we did in our reactants. Well, what happened to all that energy that's been lost here? Well, of course, it's been released to the surroundings. So temperature increases. It's been released as heat energy. So what do we know in terms of delta H here? Well, H, of course, is the energy stored within a chemical system. We can see here that the energy stored within our system between the reactants and products has gone down. So we can label our delta H here like so. So this is our delta H, the difference in enthalpy. This is the enthalpy of our reactants. This is the enthalpy of our products. It's gone down. So what can we say here? Well, in an exothermic reaction, okay, so exothermic, delta H equals a negative value. So in any exothermic reaction, your delta H is going to be negative. So how do we look at the flip reverse of that? How do we look at endothermic reaction? What's this going to look like for an endothermic reaction? Well, you're probably ahead of me. So I'm just going to draw that energy profile diagram for our endothermic reaction. Okay, so this is the opposite of what we saw in an exothermic reaction. We have the energy stored in our reactants is lower than the energy stored within our products. The enthalpy of reactants is lower than our products. So what's happened here is that enthalpy has increased as the reactions proceeded. So the reactions happened and all of a sudden our products contain more energy. Where did that energy come from? Well, they've absorbed energy from our surroundings. So what they've done is they've absorbed that energy in the form of heat, so you'd expect the temperature to go down. So as this reaction has happened, it's sucked in heat energy from the surroundings, so the temperature that we're measuring, let's say with a thermometer, is going down. So our delta H is the difference between here and here. So this time, delta H has actually gone up. So for an endothermic reaction, our delta H values are always positive. Okay, so we have a positive delta H value for an endothermic reaction. Okay, so just so you understand what's going on with enthalpy. Enthalpy, energy stored within a chemical system, within bonds. The enthalpy change, which we can measure, the heat energy exchange with the surroundings in a reaction at standard temperature and pressure, and know what standard temperature and pressure is. Okay. Now the difference between an exo and endothermic reaction, exothermic temperature increases, but delta H is negative, okay, because heat energy has been lost from the system into the surroundings, causing the temperature to go up. Here we have the opposite. Delta H increases, okay. We have a positive value for delta H. it's absorbing energy from the surroundings, so temperature goes down as it sucks the heat energy in from its surroundings. These energy profile diagrams are really useful when it comes to helping explain that. Okay, it's why I'm showing you these, so be prepared to be able to draw these and label these in an exam. And they're also used for helping to explain rates of reaction as well. So these are very, very handy things to note. Okay, so that's what enthalpy and enthalpy change is all about. And over the next few tutorials, I'm going to be talking to you about specific enthalpy changes and indeed the reactions that go along with them.